Assalamu alaikum. I am Namra Afzal from BS Chemistry and the topic of my presentation is flame retardant finishes. Starting from introduction, flame retardants are chemicals which are added to manufacture materials that inhibit or delay the spread of fire. The term retardant describes a function rather than a chemical class. Flame retardant finishes for textile which would otherwise ignite and burn in air have been recognized for many years, but since the Second World War they have become firmly established. This is a consequence of recognition of flammability hazard posed by textiles and need to produce effective and durable finishes and treatments which have minimal impact on desirable features such as handle, comfort, and general aesthetics. Modern finishes from flame-resistant cotton and viscose use reactive chemicals that are combined with resist resins. A solution or dispersion of the mixtures of chemical is spread onto material. This is then dried, cured, and possibly washed. This type of chemical finishes of cellulosic good is extremely swear and invariably has an influence on the dyes present in fibers. Both the color and the color fastness properties may be affected. These types of finishes often give products with a harsh hand and the use of softening agents is common. Alternatively, to avoid stiffening of the fabric, the chemicals can be applied using a cold pad batch method. They give a flame resistant finish with good washing fastness. Many are known by their commercial names as given. Hazards of burning textiles. The hazards posed by the textile may be exemplified by the tragic fire in Saudi Arabia on 16 April 1997 during the Hajj, killed over 340 pilgrims as flames swept through a tented camp at Mina within the vicinity of Mecca. In addition, many other pilgrims sustained burns injuries as fire spread quickly through the estimated 70,000 tents. It is most likely that all the tents were fabricated from woven cotton and that the fire was a consequence of highly flammable behavior of cotton, which was aggravated by hot, dry environment, the high winds present, and the denseness of pitched tents. During the Hajj in 1998, flame retardant tents were used in order to decrease the chance of repeat of such an incident. Cotton and cellulosic textiles in general, while being among the most flammable of materials, may be rendered flame retardant by well established means. Cotton is the most commonly used of all textile fibers, and with regenerated cellulosics such as viscose comprising 60% of world's annual fiber consumption. Because of the availability of usefulness of cotton and cellulosic fiber and their relative ease of flame retarding, they are unsurprisingly the most common used flame retardant textiles. Flame retardant cottons and viscose probably hold 80% or so of the total flame retardant textiles market. Over conventional textile fiber burns, although to varying extents determined by their chemical consumption, composition, and whether or not they are thermoplastic. Classification of flame retardants. Flame retardants are classified into three classes: primary retardants, synergistic retardants, and adjunctive retardants. Primary retardants are phosphorus and halogen based. Synergistic retardants have a retarding effect alone but improve retardancy of another when combined, and adjunctive retardants that exhibit their activity through physical effects. Burning and flame retardants. The four important temperatures when considering the flame retardancy of fibers is glass transition temperature, melting transition temperature, temperature of pyrolysis, and temperature at which combustion occurs. As shown in this table, there are some fibers and their four important temperatures are given. Flame retardant strategies. Figure given at the last presents the combustion of any textile as a feedback mechanism in which fuel from thermally degraded or pyrolyzed fibers, heat from ignition and combustion, and oxygen from the air features as the main components. In order to interrupt the mechanism, 5 modes, 1 to 5, are proposed and flame retardancy may exert one or more of these. Each stage with the relevant flame retard action is given. First one is removal of heat. High heat of UV and or degradation or dehydration, for example, inorganic and organic phosphorus containing agents, aluminum hydroxide or aluminate trihydrate in back coatings. Enhancement of decomposition temperature, not usually exploited by flame retardants, more usual in inherently flame and heat resistant fibers. For example, aramids. Decreased formation of flammable volatiles, increase in char, most phosphorus and nitrogen containing flame retardants in cellulose and wool, heavily metal complexes in wool. Decreased access to oxygen or flame dilution. Hydrated and some char promoting retardants release water, halogen containing retardants release hydrogen halide. Interference with flame chemistry and or increase in fuel ignition temperature. Halogen containing flame retardants often in combination with antimony oxides. And this is the table. From above, it can be seen that some generic flame retardant functions in more than one mode, and this is true of most effective examples. Some flame retardant formulations in addition produce liquid phase intermediates, which wet the fiber surface, thereby acting as both thermal and oxygen barriers. The well-established borate or boric acid mixtures act as in this manner, as well as promoting char. In order to simplify the clarification of different modes of chemical flame retardant behavior, the term condense and gas or vapor phase activities may be used to distinguish between them. Thermoplasticity. Whether or not a fiber softens or melts determine whether it is a thermoplastic or not. Thermoplasticity can influence considerably by how a flame retardant behaves because of the associated physical change. Conventional thermoplastic fibers like polyamide, polyester, and polypropylene will shrink away from an ignition flame and avoid ignition. This can give the appearance of flame retardancy when in effect if the shrinkage was prevented, they would burn intensely. This is so-called scaffolding effect is seen in cotton or polyester and similar blend where the molten polymer melts onto non-thermoplastic cotton and ignites. Similar effects are seen in composite textiles comprising thermoplastic and non-thermoplastic components. Flame retardant chemistry. Chemical reactions can occur both in condensed and gas phase mechanisms. Chemical effect condensed phase. Two types of reactions occurs in this phase, polymer breakdown and charring. Polymer breakdown. Flame retardants accelerate breakdown of polymers, which leads to the pronounced polymer flow that reduce the effect of flame that breaks away. And in charring, retardants cause carbon layer on polymer surface, then generating double bond on polymer, forming carbonaceous layer, and they can occur by dehydrating action of retardants. Second is chemical effect gas phase. Retardant degradation products stop the radical mechanism of combustion process that takes place in gas phase, and then the exothermic reaction stops and system cools down. Therefore, flammable gas supply is highly induced and the radical mechanism is given. In which the high reactive radicals, hydroxide and hydrogen can react in the gas phase with other radicals such as halogenated radicals resulted from frame radicals retardant redegradation. This reaction produces less reactive radicals than slowing combustion down. Flame retardant mechanisms and char formation. Flame retardants then function in the vapor phase, sharing the advantage that they will decrease ignition propensity and aid in flame extinction of any textile fiber forming polymer. This is because once the volatile products of fuels formed from thermal degradation enter into the oxidative reaction with oxygen in flame, their chemistries are similar. The starvation of oxygen and generation of interfering free radicals, for example, will assure the flame retardants' effectiveness. Antimony halogen flame retardants are most successful within both the bulk polymer sectors and black coated textile areas based on cost and effectiveness. Unlike the fiber reactive, durable phosphorus and nitrogen containing flame retardants used for cellulosic fibers. They can be applied topically in a resin binder, usually as a back coating. For textile, most antimony halogen systems comprise antimony oxide and bromine containing organic molecules such as deca bromodiphenyl oxide or hexabromocyclododecane. On heating, these release HBr and also the radicals interfere with flame chemistry by following general scheme where these radicals are apart from flame oxidative chain reactions that consume fuel and oxygen. Interfere with free radical reactions. Free radicals provide energy for process to continue. Material at gas phase mechanism has halogen containing compounds. When exposed to heat, those compounds produce hydrogen halides that form less reactive free radicals and reducing energy provision to combustion cycle continuation. Now, durability of retardancy. Applied retardants can be durable or non-durable. Non-durable. There are many applications where non-durable flame retardants are adequate. For example, on drapery upholstery fabrics that will not be laundered and durable. There are applications where durability is important, such as firefighter suits, children's sleepwear, and tetrakis hydroxymethyl phosphonium chloride prepared from phosphine from formaldehyde and hydrochloric acid at room temperature, and it contains 11.5% phosphorus. Now coming towards the flame retardants for some fibers and blends. First one is flame retardants for cellulose. When cellulose fibers are heated, three classes of volatile chemicals are generally at pyrolysis temperature 3500 degrees Celsius. Flammable volatiles including alcohols, aldehydes, and alkanes, flammable gases such as carbon monoxide, ethylene, and methane, and non-flammable gases such as carbon dioxide and water vapor. If oxygen is present when the pyrolysis products reach and exceed the combustion temperature, oxidation takes place, burning, and volatiles are converted to carbon dioxide and water as shown. The formation of small depolymerization products called levoglucosan. Levoglucosan is and its volatile pyrolysis products extremely flammable materials and are main contributors to cellulose combustion. Retardants. Those compounds which can reduce formation of levoglucosans, soluble compounds such as borax, sodium phosphate are used. A mixture as given below is found to be effective for this finish, including borax 50 parts, boric acid 35 parts, and sodium phosphate 15 parts. Only 5% solution of mixture is used, and most of fireproofing agents can be fixed by synthetic resins. Tetrakis hydroxymethyl phosphonium chloride is most important commercial derivative and is prepared from phosphine, formaldehyde, and hydrochloric acid at room temperature. It contains 11.5% phosphorus and applied by pad dry cure and used with urea and melamine produced good wet fastness flame proofing properties. The fabric is padded through solution containing tetrakis hydroxymethyl phosphonium chloride 15.8%, methylol melamine 9.5%, triethanolamine 3%, and urea 9.9%. Dried and cured at 140 degrees Celsius for 5 minutes. The process is known as probe and finishing. Second is flame retardant finish for wool. Wool is inherently a flame retardant fiber. Clean wool will pass most horizontal burning test, although open pile structures fail carpet test. Wool is blessed with high temperature of 6800 degrees Celsius and limiting oxygen index values. However, flame retardants can improve the burning characteristics of wool fabrics. Non-durable treatments which are effective on cellulose are also effective on wool, such as boric acid or borax phosphates and sulfamic sulfuric acid. Durable system based on THPC are also applicable to wool. An inexpensive durable system based on titanium and zirconium complexes have been introduced, which is unique to wool. First one is chlorandic acid and tetrabromopethalic anhydride. Chlorandic acid and tetrabromopethalic anhydrides will exhaust into wool fibers. Add-ons of 6 to 18% give good flame retardancy, dye compatibility, and are reasonably durable to drying cleaning. Second is titanium complexes. Titanium chloride is an effective flame retardant agent for wool. In the presence of an alpha hydroxycarboxylic acid, a stable complex is formed which almost completely exhausts when applied at a pH less than 3.5 at the boil, and it is important to not allow the titanium to hydrolyze to titanium dioxide, because as titanium dioxide, titanium is ineffective, and the process is good for wool used in protective clothing, carpets, and upholstery, and titanium complexes yellow wool. And third is hexafluorozirconates. The need to boil wool to exhaust titanium and zirconium chelates leads to felting, low dye fastness, and is energy intensive. To overcome these deficiencies, the 205 IWS International Wool Secretariat developed a process based on titanium and zirconium hexafluoride known as ZIRPRO process. Hexafluorotitanates and hexafluorozirconates are extremely stable in acid solution and exhaust onto wool well below the boil. The titanates, yellow wools, so the zirconates are preferred commercially. Potassium fluorozirconates at pH less than 3 give 77% exhaustion at 500 degrees Celsius and 30 minutes at 700 degrees Celsius give good leveling. A bath containing 3% potassium fluorozirconate, 10% to 37% hydrochloric acid for 30 minutes at 750 degrees Celsius give rise to a wash, fast, light, fast, and improve heat and flame resistant fabric. Pad batch and pad dry application process may also be used, and it is accepted that the hexafluorozirconate ion is bound to cationic wool in the same manner as acid dyes. Flame retardants for polyester. Polyester fabrics, being thermoplastic, will melt and shrink away from heat source, allowing some fabrics to pass particular tests without any treatment. Certain tests, however, have a melt drip specification to meet, so finishes will be needed. The flame retardants that work best for polyester are halogenated compounds that function in vapor phase. One of the best products to serve this process was Tris 2,3-dibromopropyl phosphonate. The product offered good flame retardancy, acceptable fabric hand, and good durability to repeated laundering. It passed the children's sleepwear requirements, and it could be exhausted from a dry bath or applied by the pad dry thermosol method. It is on the regulated suspected carcinogen list, and this finding came after the product had been on markets for several years, causing several billion yards of treated fabric to be recalled by Consumer Protection Agency (CPSC). The fabric producer was stuck with this inventory, and there are many halogenated compounds that improve polyester's flame retardancy. And the trick is to apply the finish so that it doesn't affect the fabric hand and still be durable to repeat launderings. Basically, there are two methods of applying finishes. One method will bind insoluble compounds to surface of fiber. Finely grounded particles are dispersed in water and glued to the surface with the binder. And the second method is to find materials that are soluble in polyester fiber and apply them as if they are dispersed dyes. They can either be exhausted out of the dye bath or patted, dried, and thermosoled, and listed below are several which have found some commercial success. First one is decabromodiphenyl oxide. Decabromodiphenyl oxide is solid material melting at 300 to 350 degrees Celsius and which contain 83% bromine. It is sold as water dispersion and is applied with a suitable binder to impart effective and durable flame retardancy to 100% polyester fabrics. There are many commercial formulations on the market differing in the blend of antimony oxide. One formulation, a 2:1 mixture of decabromodiphenyl oxide and antimony trioxide is effective on polyester. Disadvantage of DB-DPO are high add-ons needed for optimum retardancy and the stiff, boardy, and imparting due to the level of binder needed for durability. Additionally, the product is a white finely divided pigment which causes a loss in color yield. Second is Tris 2,3-dibromopropyl phosphate. It can either be exhausted out of the dye bath or applied by the thermosol process. Hydrolysis products were found to be potentially carcinogenic and the product has been banned from use. All the fabrics treated with Tris have been recalled by Consumer Protection Agency. And third is Anti-Blaze 19T. This product is a cyclic phosphonate containing 20% phosphorus. It is a clear wear soluble oily liquid, and it can be applied by pad dry thermosol process. Because of its high water solubility, it does not exhaust from a dye bath. Heat treatment causes the hand to stiffen and the finish is durable to repeated launderings. Now there are three approaches to flame retardant polyester: additives to polyester melt, flame retardant copolymer, and topical finishes. Additives to polyester melt. To combine molten state of retardants with polyester melt and extrude them together via spinet, or to melt polyester and combine it with molten retardants together. Second is flame retardant copolymer, to combine another retardant synthetic polymer with polyester and extrude them together. And last one is topical finish, to improve retardancy after being produced by applying surface treatment with flame retardant compounds to form film of retardants and separate topical finishes. Now there are flame retardants for some fiber blends. Providing flame retardancy for blends is not easy task as we did for single fibers. The blend's flammability is worse than flammability of their components. The question arises, what happens to the blend when exposed to flame? The natural fiber form cold when exposed to flame, and synthetics one melts. The melted fibers gets held by cold formed by natural fibers and make them ready to burn. The flammability of blend exceeds the two components. Mechanism demonstration. The flame retarding mechanism for blends can be demonstrated by using limited oxygen index value. Let's get introduced to what limiting oxygen index value is. It is content of oxygen and oxygen or nitrogen mixture that keeps a sample at limiting of burning, used as an indicator of flame retardancy of fibers, and those fibers having limiting oxygen index greater than 20 are thought to be flame resistant than those which have lowered their value. These are limiting oxygen index value for common fibers such as polyvinyl chloride, wool, polyester, acrylic, polypropylene, and cotton. Now question arises, why May 20? It is known that oxygen content of air is 20%, then the oxygen need to burn material has to be higher than this. Those fibers having limiting oxygen index approaching 20 burns easily, whereas those having more than 20 take too long to reach at pyrolysis temperature than burn less. How to make the blend flame resistant? For cotton or polyester blend, decabromodiphenyl oxide in combination with antimony trioxide is most common. It has drawbacks as well. Need for higher add on up to 37% with binder as softener. The application can affect color and hand of finished products and higher commercial cost. Intumescent. This is the generation of expanded foam char formed by heat and special additives. The additives includes char formers, catalysts that yield inorganic acids at about 150 degrees Celsius and generated that provide non-flammable gases for foam and binders for fixation to fabric. The process. The system provides a foam insulation layer on the fabric surface, as in cotton, wool, and basophil fibers, provides all flame retarding requirements such as preventing retarding further flame and flame barrier formation. Some of most common tests such as 16 CFR 1610, it is used for general apparel and fabric is held at 450 to flame per second and so on. Problems with flame retardants. Side effects to fabric physical properties and toxicity of some flame retardants. First one is side effects. Flame retardant finishes were found to have an impact on physical properties of material, especially when added in higher amount. Some of the problems, they may cause harsh hand, loss of tensile strength, and color effects, fabric yellowing, and dye shade changes in case of durable finishes for cotton. And the combination of with other finishes such as softeners, easy care, and repellent finishes must be carefully tested. Toxicity of some flame retardants. Most common in halogen and metal ion-based retardant, phosphorus, antimony, and zirconium compounds in the wastewater. Formaldehyde released during curing of a permanent flame retardant finish of cellulose, and free formaldehyde of finished fabrics, storage and transport. From non-permanent to permanent. Non-permanent. In this case, salts dissolved in water are applied to the fabric by padding and dried. The retardancy is lost when the fabric comes in contact with water. And permanence applies two approaches here: to bind molecules chemically by using one of its hydroxide ion, or by polymerization of products with itself forming layer in and around the fiber. In both cases, phosphorate derivatives are used. Applications in permanent flame retardants. Padding in a bath containing the flame retardant products. It is a precondensate of trace hydroxymethyl phosphonium chloride. Passage into a machine filled with gaseous ammonia, allowing a polycondensation chemical reaction to take place, and the ammonia group serves as a link between different molecules, and drying, washing and oxidation to remove unbound products and to stabilize phosphorus at 5-fold bond, and finally drying. Now there are some applications of flame retardants, including for home installation, in upholstery furnitures containing polyethylene foam, plastic casing of electronics, in carpet padding, and in some baby products like diaper changing pad. Conclusion. Fire retarding finishes impart fire spread retarding or resisting capacity to product. We can apply different retarding chemicals to impart the property depending on end use. These chemicals can have an effect on both health and physical properties of fabric. Blends retarding performance is lower than their components. The performance imparted can be temporary or permanent, and fire retardant materials have many applications in our daily activities. Silicone finish. After flame retardant finishes, there are some silicone finishes. Silicone has reached or lies in various ways and in various forms used for textile in clothing and industry. As in case of adhesives, binding additives, fabric coatings, dress linings, and thread scalers, elastomers, and rubbers are used. While for textile finishes, fiber lubricants and processed sports oils and emulsions are used. Treatment with silicone compounds provide silicone compounds impart new important cellulosic fabrics. Consumers benefit from textile based on silicone as it offers long-lasting comfort and efficiency. Now, if you go to buy jeans, you can be sure to find denim that will give you the impression of utter warmth and shape. That's how silicone affects textiles. Since use of silicone in textiles is generally important, there is still much potential to development of new silicone compounds on their mixture to improve or impart functional properties to textile materials. Silicone microemulsions. Amino functional silicones have a big importance to textile softening companies. Their surface smoothing and softening properties are above all other product groups. Micro and semi-micro emulsions can be made with specially selected emulsifying recipes using amino functional silicones. They offer a number of advantages which are totally in keeping for modern textile finishing. The low particle size micro emulsion less than 0.01 micro and semi-micro emulsion less than 0.1 micro allow for the additives to penetrate it into the fiber core, and in this way allow for an excellent product distribution of micro emulsion. Silicone micro emulsions give textiles an excellent inner softness and distinctive surface smoothness without looking greasy. They improve the technological properties of textile, support the elasticity, and optimize the sewability. Microemulsions have good product stability and decrease the hazard of roller coverings. The use of fast-running machines, devices with high shearing force and may cause problems when working with silicone microemulsions, unless specially optimized products for this application field were selected. The softening capacity of silicones is based on gliding behavior of fiber surface as well as in fiber. Polydimethyl siloxanes attached to amino functional groups allow for a better orientation and sustainability of silicone on substrate. This again leads to a better soft handle, super soft, and good washing permanency. This is the fixing and orientation of amino functional polysiloxane on CAL fiber, cell fiber. Comparison of performances of macro, micro, and nano silicone softeners. A lightweight plain woven scoured and bleached cotton fabric was treated with macro, micro, and nano silicone softeners, each at 3 levels of concentration separately. The treated fabric samples were tested for hydrophilicity and various physical properties to evaluate the performance of softeners. By using ANOVA analysis of variance, it is established that there were significant changes in degree of hydrophilicity, crease, recovery, stiffness, bending modulus, drape, as well as tearing strength. The macro softener made the fabric less flexible and less hydrophilic in nature. Then the same with the micro, and the micro softener imparted maximum flexibility and nano softener the best hydrophilicity. The softness evaluated subjectively by the judges confirmed that nano finished sample produced maximum softness and maximum durability, followed by micro and macro finished samples. The scanning electron microscopy photographs confirmed that the macro softener mostly deposits on the fiber surface, while the nano softener penetrates inside the fiber and micro softener takes up an intermediate status. Dichlorodimethyl mediated one-step synthesis of hydrophilic and hydrophobic silica nanoparticles. Hydrophilic and hydrophobic silica nanoparticles were synthesized by cheap, simple, and low-temperature one-step method. The method involves a catalytic reaction between ammonium hydroxide tetraethyl orthosilicate and dichlorodimethyl in an ethanol solvent. The effects of different parameters such as chemical concentration, reaction temperature were investigated on size of synthesized silica particles. Characterization of hydrophilic and hydrophobic particles were performed using dynamic light scattering, X-ray diffraction analysis, transmission electron microscopy, scanning electron microscopy, Fourier transform infrared spectroscopy, and thermogravimetric analysis. According to the results, by reducing the amount of ammonium hydroxide, ethanol, and temperature, the size of hydrophilic silica particles can be reduced to 10.4 nanometer. Other sides, addition of DDS agent caused to silica particles found hydrophobic property, and the size of particles reduced to about 6.5 nanometer. Polyurethane resin for textile finishing. When you pick up a shirt from your closet and put it on, think about why your shirt doesn't need ironing. That is because there is a water-based polyurethane resin as a permanent care finishing agent with good film forming and elasticity is expected to give the fabric a certain wrinkle resistance and improve the fabric strength. Can greatly improve the finishing, wrinkle recovery, angle, wear resistance, and give the fabric a good feel. It is effective for cotton, polyester, viscose, and other fibers. Keep your shirts neat and wrinkle-free every day without the need to iron them every day. In daily wear application, fabric cannot maintain its unique shape memory for a long time, especially after repeated washing. The wrinkle resistance is greatly lost. After years of research, it is found that the waterborne polyurethane as a fabric coating finishing can achieve good effect in fabric anti-wrinkle treatment, and the coating shape memory performance is excellent. And waterborne polyurethane with water as the dispersion medium, environmental pollution, low cost, so it can be used in fabric. Coming towards the environmental issues. Flame retardants constitute a large and diverse group of anthropogenic environmental contaminants used in numerous applications, including the manufacture of electronic equipment, textiles, plastics, polymers, and in car industry, primarily to protect materials against ignition. Among different flame retardant groups, the brominated flame retardants are the large market group because of their high performance, efficiency, and low cost. Recent reports have demonstrated the presence of brominated flame retardants at various concentrations in air, water, soil, wastewater, and sediments far from locations where they are produced. Moreover, the traces of brominated flame retardants have been found in plants, wildlife, and even in human samples. Thus, recent publications on the persistence of bioaccumulation and toxicity of some brominated flame retardants are a source of great concern. Despite the information available on brominated flame retardants distribution and many questions related to expiry, metabolism, and environmental occurrence and behavior remain unanswered, remediation of contaminated sites by physical chemical process is expensive, labor intensive, and often results in shuffling toxicants from one place to another. A possible solution to this problem is thus controlled, targeted biological treatment, taking into account The limited formation available today or more research is needed regarding the fate and impacts of flame retardants in the environment. Since certain abiotic and biotic processes can change compound characteristics and make them more persistent and toxic, it is important to investigate and understand the detailed biochemical transformation and degradation pathways. The microorganisms involved, the potential derivatives and intermediate generators. These are the references which I have used, and that thank you so much. That's all from my side.